We're the autonomous golf cart team. Our project is for our project sponsor, Dean Kumar, Associate Dean Adversary, and the SDC Foundation.
All right, my name is Paul Shadi.
I'm Braxton McGrath.
I'm Brady Gordon.
Caleb Lovner. So to introduce our project, we're tasked with creating a fully autonomous golf cart and be around campus. We're really excited to showcase the capabilities of the mechanical engineering department and to provide transportation to all faculty members and visitors to tour our beautiful campus. We'll also serve as a way for people with mobility issues to get around campus and to allow everybody to see our beautiful campus here.
Moving to our main goals. So the first one, we must get a golf cart and integrate all of the system in the golf cart. So we're talking about system, sharing system, camera system, all of that. So for the second option here, we have we need to integrate camera based with AI navigation on our golf cart. So this is to provide a smooth and reliable control on our surrounding. So on the third here, the golf cart must be able to autonomously control acceleration, deceleration, and braking the steering. So number four, we must centralize control on onboard in electronics. So we're talking about our human machine interface. So number four here, we must integrate safety system in our golf cart.
So before we get into our specific design solutions, we kind of want to look at where the process of autonomy has gone, specifically in golf carts. So starting with the SMART team, the Singapore MIT Alliance for Research and Technology. So this video kind of shows what they were capable of doing in 2013, I believe it was. And kind of what they did is they obviously outfitted it with everything to autonomously steer, brake, and accelerate. But their primary form of navigation was LiDAR-based navigation. They were able to do this by creating a LiDAR map with a vehicle that they drove around in the area that they had wanted to operate this in beforehand. And so really what this does is it allows the golf cart to process and recognize where it is based on the information that the LiDAR sensor is giving it. But the main pitfall of this is that it only allows the golf cart to be operated in a space that has been previously mapped out by a vehicle that went ahead with a LiDAR sensor. We kind of want to move into the future with our golf cart and do something like this company here. This is a company called Cart EAV. They specialize in leasing autonomous golf carts to private communities and neighborhoods. And what they are able to do is they have a completely camera and GPS-based navigation system. And that allows for the quick transfer of these golf carts to many different environments, but specifically allows the golf cart to be used in an environment that hasn't been previously mapped out by some other vehicle. And then speaking of the camera navigation system, so this is a example of a camera that was mounted on a golf cart and driven around. Then a software was used, the machine learning software was used after the fact to be able to process and identify what the camera is actually seeing on the golf cart. And so this, as you can see, the vehicle is highlighted in blue, the sidewalk that it's driving on is highlighted in pink, the leaves in the trees are highlighted in green. So it's kind of recognizing everything that it's seeing and identifying that through a machine learning process. But we want to move sort of into the future with this as well. So we're looking at a company called Stereo Labs. They make a vision system using the ZX camera and the Z box. And what you can see here is it's a much smoother and much more practical way of identifying what we're looking at. So the green is where you can drive, the red, obviously, things you don't want to run into. And it just provides us a better way and a more streamlined way of identifying where we can keep the golf cart.
And speaking of these cameras, here is the ZX camera they decided to go with. It's a 2-camera system, so it's a stereo camera. It allows it to then have a 120-degree field of view using both those cameras at once. And then we plan to use a couple or 3 to get a wider view of the golf cart. That would be also be able to look at what's in the reverse if we have to go into reverse. But the EZX camera allows us to look out to 65 feet in advance. We can see all that is coming up to us at a time. And then using those cameras, this ZAI box is what determines like where we can drive. So like the green and the red that we saw, this is what it's making. Using that image processing, we can see where we can go, where we can't go after we tell it. And then on the left here, we have our rough wiring diagram for now. And Cole is going to explain that for us real quick.
The foundation of our system here is the ZAI box and the additional chips that we're going out. Those are both high-powered AI processors, and are going to allow the system to take the camera inputs and output it to the other jets, and where it can then relay to difficult systems like the other actuators and for have feedback loops. And also it will run our safety systems to make sure everything is running safe and working together seamlessly.
So we're looking at testing all these cameras without actually having the cameras here. So this is a simulation software called Isaac Sim. And in this top left one here, this is what we see when we load up the simulation software. So we've made a box with wheels to represent our golf cart. We've made the wheelbase, we've added the camera in, and we've added rotation to the wheels so we can move. So also with the Z box, it can tell us that we're at this location. So when using this system, we have the camera in, and then it goes to another part of the simulation software called RViz, and it allows us to see that the camera sees the depth map, and then using these, it makes a point cloud, which the point cloud is it's seeing in 3D space where it's at, so that way it can know where it's at a time in the 3D space. And then the camera view, obviously, it's the stereo, so we can see it's using both of them at the same time to see that 120-degree field of view. And then the depth map is showing like where everything's at, so we can map that in the 3D space for the point cloud.
Yeah, to actually control the motion of this golf cart, we have two systems that we're going to need to integrate, and that's to autonomously brake it and autonomously accelerate. So for the braking of the solution that we've come up with, we're going to attach a block or a stopper to the brake cable of the golf cart. And then we're going to have a linear actuator in parallel to the brake cable. And what this will allow us to do is push against the stopper without actually having the linear actuator attached to the brake cable. So we'll be able to brake with using a linear actuator, but it won't have to be connected to the linear actuator. And essentially the idea behind this is that we can still have the manual use brakes available to any user in the golf cart, but also if the golf cart would need to be driven around manually, they can still be used without any modification to the golf cart. And then the second system, the throttle control system. So all club cars, model year 2000 up, are outfitted with these M-Core sensors. They're motor controller output regulators. And essentially what they are responsible for is receiving the throttle pedal input and dictating the throttle percentage based on the amount that the throttle pedal moves. So you can see the black M-Core up there. It has a small round input into that, and you can see how it kind of fits into the system there. And as the throttle pedal is pushed, it activates a micro switch in the M-Core, and that actually tells the golf cart motor controller that there is signal being sent there. And then as it's pushed further and further, the M-Core uses a potentiometer to essentially convert this rotary motion into a varying voltage signal that will tell the motor controller what sort of throttle percentage is needed to accelerate the golf cart. And this would also allow us to be able to control the voltage signal going to the motor controller without actually interfering with the pedal setup, and we will be still able to use the throttle pedal and the brake in manual format.
So the next system that we need to automate in the golf cart is the steering, and the design choice we decided to use is also using a linear actuator control steering, which is essentially a piston that moves in and out depending on different voltage levels, and newer ones can actually have the distance that the linear actuator moves in and out based on a certain voltage level. So in this video shown here, this is kind of the idea that we're going to go with. We're going to have the linear actuator mounted in parallel with the tie rod of the golf cart. And as that linear actuator moves in and out, that's actually going to control the direction of the golf cart. And then using that mapping, we can actually determine the maximum left and right steering values of the golf cart using that linear actuator. And that information is going to be relayed from the cameras to the secondary adjustment, and that's going to determine where the golf cart needs to make certain adjustments depending on different obstacles in the pathway or making different turns. And the design choice that we made so far is to use a progressive automation PA10 actuator. This is an actuator that has 450 pounds of force, which should be more than enough to allow us to dry steer or move drift steer while moving. And we've also decided to mount it on the front right of the golf cart. Picture there. Similar to how this is done in this video, and that will allow pretty seamless steering in conjunction with the jets and boxes. So after we have all these three different systems, the braking, the acceleration, and the steering automated, what we're going to have to do is allow the user to actually use the autonomous golf cart. And the way that we would like to do this is have a computer tablet with access to Windows as well as data connection to choose the different locations on campus using this tab here, where you can simply press a button and go to the different places you'd like to go on campus. And so far, a couple of different mounting options that we have so far are up on the top here, which is the bottom left picture. And this is actually what Clubcar does for the tablets that they install on theirs already to show golf course maps. And then the top is also an idea that we can have is where we can have a custom mount in the center where the user can decide where they would like to go. So we have made some progress on the mapping so far using OpenStreetMap. So far, our current progress is pretty decent. We have a system where you're able to choose your starting location and then go to an end location coordinates. The only problem with this so far is that it still is pretty rudimentary. It has to be done in a Python script so far, and then it takes you to a third-party website that creates this map, and it has no communication right now with any of the other systems in the golf cart. And the final system that we would like would be something very similar to what is shown in the CSC website on how to get to different locations on campus with a much cleaner view on the map, and then also showing your estimated time of arrival, also showing the different turns and things that you will make. And this will also be outputted just from the tablet, and this will communicate to the golf cart in the different systems and show and have everything moved together for the golf carts to go.
So our final design solution is about integration safety system. So we started with the top left there. So we have the orange light. So it's technically to alert people that the golf cart is not operating autonomously on its own, like nearby vehicles. And the second, on the top right here, we have the 2D LiDAR. So this is pretty much an advanced sensor that we're going to be using that will work alongside our camera system to detect close range, movement, obstacle, and nearby vehicles. So on the third one here, we have our seatbelt. So we plan to install a properly mounted seatbelt in our golf cart to keep our rider and operator safe when the golf cart is operating. So the final safety system here is emergency stop. So this is a way for our rider and operator to stop the golf cart when they're facing an unsafe situation. So what it does is pretty much shut off. When pressing on the button here, it shut off the golf cart acceleration and deceleration in all other autonomous systems.
So taking a look at the Gantt chart, this shows what we've done throughout the year so far. So as you can see, we have our major stuff at the top here, including our presentations that we are going through. And then we can see the little smaller bits that kind of are under that big part of the presentations. There are just things that we do while we work towards the presentations. And so all of the green things that you see here are the parts that we have done so far throughout the year. And then the red parts are the things that we are moving towards, getting towards the end of the semester, and going to be starting for the next semester for testing and all everything for that.
Take a look at our budget here. Our big line items are the ZX cameras, which are about $700 a piece, and we have to do both budgeted, as well as the AI box, which is a little bit over $2,000, and our HMI tablet, which is $700. And then additionally, we have a miscellaneous wiring and other software items like our 2D safety LiDAR. Moving into the physical systems, we have our linear actuators for steering and braking, as well as the M4 accessories that are needed. We also have a $1,000 buffer in this budget just for expected items and possible cost inflation. And things like decals to show our SDC logos on the car. This brings our total to a little bit over $7,000 for technology. And we also have a sponsor to the foundation for the belt part.
Any questions?
I've done some of this before, and what I would suggest is that the mapping software, basically you need to understand where the destinations are, and then understand or create a graph of the paths that are sort of allowable paths, let's call it that. And then when you say, I want to go from here to there, now your system can pick a path pretty easily and just go there. So I would integrate that mapping, a lot closer to your destination. So there's an algorithm called A star. Look up A star, and that's actually the graphing algorithm that'll get you.
Thank you.
Also, I have a question because you are designing a golf cart. Could you just summarize or outline list of features that set your golf cart apart from the existing ones?
Well, I guess the main portion of the difference is that we're doing this on a budget essentially, and we're doing maybe what has been done before by other companies such as Cart EV in essence, but we're doing it in a much cheaper fashion. And I guess the other main difference would be that we're using these said cameras, which are specially designed for autonomous navigation and human tracking. So it takes a lot of the guesswork and pain out on our end. We're able to just use the X cameras, with the Z box, with the SDK software, and that kind of it's all-encompassing autonomous navigation, human tracking, obstacle avoidance software package, all of it. So I guess using that, we're able to accomplish this much cheaper and much faster than maybe anybody else would do.
Also, another thing is us being on a campus, we have much smaller, so we're sticking to the sidewalk. Most like Cart E2E they deal with is they go on the roads. If they choose the places like Florida, like the communities like that, they allow them to go on the roads. They have a bit more space and they're more watching out for cars in that essence instead of people to us. So that's also what kind of sets us apart from the company like that.
Thank you.
Great presentation. Definitely looks like you're on your way for a digital twin. And Isaac Sims, good to see that. What's the timeline look like for a full digital twin in your testing in Isaac Sim on a topic?
So right now, this is one of our action graphs that we have going on at the moment. So this is right now mostly to control the golf cart. This is our WASD. This is for that. So right now we also have another action graph that allows it to connect to the RViz. And our next steps are moving. So putting these cameras in so that then this object avoidance, that's our next step. So which we are getting a lot closer than we have been to getting that all that initial testing with the cameras and everything done for that digital twin we speak of. Cool.
Yeah, so one of my questions is that like, is your system able to be driven in like different environments such as like rain or snow, like for the prototype, so to speak?
We're gonna try to do this in fair weather or canvas it out for the best change. We do have polarized lenses, which will help with outdoor environments. We also have restrictions on the box. It's rated for 32. We won't be using them very much.
So you ready?
Something that we probably could include as a stretch goal. I think for now. Our goal is to mainly achieve the full autonomy of the golf cart and get that in working condition before we add any sort of additional features like that. I think at the current time, the plan for sort of a mandatory warning would just be on the screen itself and just making sure that the screen alerts the riders that it's about to start. And also the operators of the golf cart will have to be trained operators as well, due to campus policy and just it's a good safety practice. So the operator will also be able to alert the riders that the cart may be.
Are there extra steps to integrate the Z software, or is that pretty much plug and play since that's what it's custom built to do?
At the time, it kind of seems like it's mainly plug and play. The Z box comes preloaded with the Z SDK software. And so essentially all we really have to do in theory is create this digital twin model and put it in different scenarios that we might face on campus, such as a human running out in front of it or interfacing with another vehicle on the sidewalk or people on the sidewalk, and just put it in all these different scenarios. And then we actually will use Z SDK software on our simulation setup to be able to process these image outputs and sort of decide what the golf cart will have to do in that scenario to respond accordingly. And then just run those scenarios over and over again in a repeated fashion. And eventually we'll determine what to do in every scenario. And then that's essentially called training a classifier. And then we upload that classifier to the Z box. And then that's what will be the brains